Hello, everyone. My name is Georgy Kucherin, and I'm a security researcher at Kaspersky's Global Research and Analysis team, where I help tackle the most complex threats out there in the world. And today, I would like to talk to you about DLL side-loading. Now, before we start, can you please raise a hand if you ever experienced DLL side-loading, if you know what it is, or if you think you know what it is? OK, thanks. So, since not all of you raised hands, I'm going to do a quick explanation here. So DLL side-loading is basically a way of launching a malicious DLL inside a signed legitimate process. So you have a legitimate process, and then you make it load your malicious DLL that you supply to it. And as such, the malicious DLL gets running inside a legitimate process. Now, why would you ever do this? Because security solutions, they are sometimes, they are always, optimized for speed. And sometimes they may trust processes which are spawned by legitimate executables. They can trust them more than processes that are unsigned, by the way. And these processes that are launched through signed executables, they may not be monitored very thoroughly, and that allows you to launch malicious code in a more stealthy manner without it being detected by a security solution. So let me show you how this works. Over here, I have this file called file.exe. And if we examine its properties, the digital signatures tab, we can see it is signed by Avast, which is a cybersecurity company. But now, let's try to launch this file and also log its activity with a tool which is called Process Monitor. I enable logging and launch the file. And if I scroll down, I see that this executable tries to load a DLL called wsc.dll. It tries to locate it from different folders around here. And now, in the Documents folder, I have a prepared malicious DLL, wsc.dll. And now, if I paste this DLL into the same folder as the executable, and if I launch the executable, we see a pop-up. It means that our malicious DLL is now working, and what it simply does, in our case, it simply launches a pop-up that says that the DLL has been injected into this process successfully. So this is how it works. And we just saw that while loading this DLL, Windows tried to locate this library, wsc.dll, inside several directories. Now, let's try to find out what these directories are. And if we search the Windows API documentation, we can find out that it specifies the order in which DLLs are searched when they are loaded. And here we can see point 7, the folder from which the application is loaded. It is one of the places where these DLLs are searched, and the others being the system directory, and there are other directories being searched. In our case, we put our DLL in the same folder as the executable file, the application file, and we got our malicious code executed. Now, remember I said that the DLL side-loading technique occurs only when executables are vulnerable. So now, let's now talk about what makes a specific executable vulnerable to DLL side-loading. It happens when the executable loads a DLL using a relative path. For example, here, the call to load library is the first one. It specifies only the file name. It is a relative path. But the second one, it contains a full path. See Windows System 32. When we try to load the DLL using the full path, nothing happens. And indeed, let me show you this. Over here, I have this executable. And it is configured to load the wsc.dll library. And if we build it, and then if we switch to the directory with the executable, and paste the WSC library inside, then we see the same thing. This is what causes the vulnerability, the use of the relative path in the call to load a DLL. But actually, if we look at the log, we can see that our avast executable uses other DLLs. For example, this one, which is called anti-DLL.dll. Let's try to sideload it too. We'll rename this file to anti-DLL.dll and launch the executable. I launch it again. However, nothing happens. For some reason, the side loading fails if we simply change the DLL name, although we see that this DLL has been referenced in the execution log. So the question is, why this happens? If we look at the order of loading DLL specified in the Windows API, we can see that before 0.7, which is about the application folder, we also have points 4 and 5, which are loaded module list and known DLLs. And if we Google what anti-DLL.dll is, we'll find out, this is from the Windows internals book, that anti-DLL, it is the first library that is ever loaded into any process, because it contains code which is necessary to start up an executable APE file. So the time we start the process, anti-DLL is automatically there. And so, by this logic, since anti-DLL is always on the loaded module list, and since point 4 here comes before point 7, can we actually ever sideload anti-DLL by putting it in the same directory as the application? Yes or no? No, yes. The answer is no, because point 4 comes before point 7, and since anti-DLL is always in the process, then we are unable to do the loading, because it terminates successfully, the process terminates successfully at point 4, which is before point 7. We never reach point 7. So, I've been asking this question to many people who are very well familiar with the Windows internals, who are very well familiar with this process of loading DLLs, and they said, no, we can't. And I thought that we can't do it this way, until I was assigned to investigate a case of an infection related to the APT41 threat actor. It is a Chinese-speaking state-sponsored actor which is known to conduct cyber espionage operations all around the world. But apart from that, members of this threat group, they also have a hobby of hacking video games, which they likely do for profit, stealing money, transferring it to their own accounts, spending it buying rich cars. That's what most black hat hackers do. And it was yet another infection of a video game company located in Southeast Asia. Luckily, the malware that attackers used, it was already well known. It was a malware called Pipemon, which was discovered by ESET in 2020. So it was just a new version of this malware, and ESET already attributed it to APT41. We agree with the conclusion, so the attribution and analysis was very simple. However, there was one remarkable technique that attackers used. The malicious payload, they put it to the following location: C Windows Microsoft.net something, and the name of the file was anti-DLL.dll, while the original anti-DLL.dll, which is a system library, should be located in System32. Now, when we have these cases when a system DLL is located not at its place where it should be, it's a jest of sideloading, because we try to somehow load the library using an earlier point in the algorithm that I showed you. So why would they need to put the DLL over here? Let's discover this one. Let's discover this thing. Over here, I have a Windows Server VM, and let's actually just restart it for now. I just want to restart it. It goes on, and it will take a bit of time, hopefully very quickly. The infection, it occurred on this Windows, on this exact Windows Server version that I'm currently running. So if we now look at what program is started, we can see Server Manager. And if we look at this slide, we can see also that the path contains Server Manager. Now, what happens if we try to put our test malicious DLL at this directory? We put it, we restart Server Manager, and we see that we have this pop-up. So they do it, they put this DLL to configure persistence on the machine. So every time the computer starts, the server starts, this Server Manager tool automatically starts up. When it starts up, it loads this DLL, and as such, the malicious code gets started in the context of the Server Manager process. This persistence technique is not described anywhere on the internet, and it's in fact unique because usually to install your malware on a machine, you need to create a scheduled task, a service, maybe add something in the autoruns folder. There are many ways. But this technique is quite unique, and since we don't need to create anything apart from this file, it cannot be in fact detected through tools like autoruns. You can only spot this DLL with a researcher's eye. So now the question. We just talked that anti-DLL is in the loaded module list, and it comes before 0.7, before checking any other folders. So the question is, how could APT41 been able to subvert the process of loading this DLL? Because we discussed it, 0.4 becomes 0.7. We said it's not possible. Then how? The answer to this question is, it's because the Server Manager software is written in the .NET programming language. And if you research how DLLs are loaded there, you will find out that it uses another algorithm of loading DLLs. Before checking the current folder, the system folder, well, it first checks a folder called the global assembly cache. And only afterwards, it checks the current folder, and then it checks the rest of the folders out there. And also, one thing which I want to talk about is 0.5 here, known DLLs. Like, known DLLs are a set of libraries, a set of system libraries, which are known to kind of never, you can never replace them with an alternate version in memory. Whenever you say, for example, I want to load kernel.c to the DLL, it's a system library, then it gets loaded from the system folder, from nowhere else. It turns out, with .NET, you can side-load this kind of DLLs too. But this happens not with all DLLs, with not all .NET versions, but only with .NET Core. So let me show you this. Over here, I have a .NET program that is designed to call the getTickCount function from the Windows API. So this is the folder with my executable, yes. And if I try to run it, then it just displays the result of the function, which is an integer. However, if I copy the kernel.c to the DLL folder, then we have a message saying that the injection has been successful. Again, if you know how DLL side-loading works, if you ever seen it in the wild, you know that side-loading a known DLL is something near to impossible. But it turns out with .NET you can do it. And actually, having spent some time doing further Googling, I found out that this issue has been found before. It was not related to known DLLs or anti-DLL.DLL like we did here. It was less serious. They discovered it on a less serious DLL. And they said, yes, .NET doesn't limit system DLLs when searching for a DLL, so Microsoft does not adhere to its own standards of security when it comes to loading DLLs, and so this is bad. Obviously, they reported the issue to Microsoft. Microsoft admitted the problem, but they said it does not meet the bar for servicing with an immediate security update. And they say it's something that we may fix later, and that's it. This was a few years ago before the APT41 attack took place. Guess if it's still fixed? No. So you see, today you see, it's a minor issue, we're not going to fix it. Tomorrow, APTs use it in their attacks. Actually, Microsoft did propose something. They do have a workaround published on their page. They added some kind of a rule which checks the program for using an unsafe DLL import search path value. What this means is that to fix this issue in your software, you need to explicitly add this line to your program. But again, it's unlikely that given this rule is not enabled by default, it's unlikely that many developers know about it. And I'll prove you that, that almost no one knows about it. And this makes lots of .NET applications vulnerable to this kind of a side loading, abusable by APTs, and the tricks I showed you earlier. And another problem is not just the software that is vulnerable, but it's the security solutions that are designed to detect DLL side loading. Imagine that a security solution has been using a machine learning module to identify which loads of DLLs are side loading and which is not. Imagine if the module never saw that these known DLLs and that DLLs that are already loaded can be side loaded. Or maybe, even worse, the model may have been trained to detect, to treat this kind of known DLLs, let's say, as benign cases, always. But we just saw that it's not always the case, which may confuse the model. And for security solutions that do not know that this kind of behavior may happen, this is a problem. And I'll show you that security solutions don't know about this fact. So yes, I've decided to investigate how serious this issue is and try to think of examples of apps, popular apps that are vulnerable to DLL side loading. And to do this, I decided to use this Yara role. Yara role is basically, in case you didn't know, it's kind of a language for signatures. And I've started hunting for applications that make use of known DLLs and that are signed and that are popular. I searched this rule, and of course, which are written in .NET. I've run a search using this rule on VirusTotal, and I got quite interesting examples. One of the applications vulnerable to this was Discord, which is a messenger. And imagine that you are a threat actor, you want to silently persist on the victim machine, and you see that they have Discord installed. Now, Discord, in most cases, is designed to launch on startup. And it runs on startup through this exact command. In it, there is a flag process start, but if you change it to process start and wait, then Discord on startup calls this function anti-query information process, which is from anti-DLL.dll. And if we do it, we can sideload this DLL and launch malicious code inside the Discord process whenever our machine starts up. To do this, all we have to do is get to the Discord folder. Now, copy the anti-DLL.dll file in the same folder as Discord. Then, we need to change in the startup, we need to change process start to process start and wait. I wouldn't think that it's something stealthy because show me a cybersecurity analyst who knows by heart how Discord is supposed to start, with what arguments it's supposed to start. And if we run Discord this way, we have an injection. So basically, a free way to run code inside Discord. Now, I remember I talked to you about security solutions, that security solutions don't know about this vulnerability or how to fix it. So there was one security solution that I found vulnerable to the thing, and it's Avira. And it caused an issue with the self-defense mechanism of this security solution. A security solution needs a self-defense mechanisms to make sure that a threat actor can't disable the tool, so that it can't inject anything into the security solution, so that it cannot terminate its process, because if you try to tamper with the security solution, it may not be able to detect the malware. And so the security solutions try to prevent any kind of a behavior that tries to terminate its processes and stuff. So over here, I have a virtual machine with Avira installed. And let's say we want to tamper with Avira's process. I'm not sure what's going on right now. OK, so here is a task manager. And here you can see the Avira processes. And if we go to the directory with Avira, the main one, if we try to copy a file, ntdll.dll, to this folder, even if we have admin rights, then we fail. However, if you move this DLL, called ntdll.dll, to the folder, to this folder, which is a global assembly cache, it's a folder unrelated to Avira, and if you restart the virtual machine, I hope it works. Because there is something with my PowerPoint right now. Let's wait for it to start up and see what happens. So even before we saw the desktop, we see our window. We got injected to the Avira process, which means that now we do it, we can try to disable the antivirus, run malware in the context of the antivirus, do whatever we want from this process. We have system privileges. We can do whatever we want. This is how it works, and there are not many companies out there who know about this trick. Let me try to restart the presentation. So the moral, like this case partially occurred because, well, you saw that Microsoft, they knew about this problem, but they decided not to fix it. And if you are a software vendor, and if somebody submits such a problem to you, I mean, all the things we covered today, they are not really worthy of CVEs, because just as how Windows security model works, we don't do any elevation of privileges, so it doesn't deserve a CVE, but still. If today you see this kind of a security-related issues that you think they're not important, someday APTs will find these issues, and they will try to leverage them to conduct cyber espionage. And when it happens, when there will be a security research articles posted about it, then they will mention your company, they will mention how you were reacting to this vulnerability. This is what you need to keep in mind. And you should also pay attention to this kind of minor issues, because they're important. Because if you fix them properly, then you give no chance for an APT to parasite on your product. So that's all I wanted to say today. I hope you enjoyed the talk. Please don't forget to rate it when you come out of the room. And if you have any questions, please don't hesitate to ask them. Thank you.
Thank you very much. Your presentation was amazing, and the insights that you share was great. We have some time for some questions. So, we got some active ones. Let's go with the close one here.
Hello, great presentation. I liked how you uh, changed back and forth from the presentation to the Windows VM. In the case when you injected into the Avira application, when it started before even booting, can it bypass the antivirus by stopping them from running at all?
Thank you for your question. I didn't really check it, but I think at least with the user mode part you can do something because you're already in the process. Maybe you can at least inject some code that would prevent any pop-ups to the user that would show that a threat has been detected. I didn't really test it until this point, but I think it's definitely a point to something because maybe you can just launch malware from this process and see if Avira can detect itself. It needs further experimenting.
Okay, thank you.
Question. Okay. Yes, the one with the yes.
Thank you. First of all, great presentation. It was really nice, entertaining, I'd say, and I've learned a lot of things from here now. One thing, would signed DLLs be a solution to this issue?
Sorry, there is an echo. Would side?
Signed, authentic code signed DLLs be a solution to this issue if implemented correctly?
If I get the question correctly, you're asking about what would be the solution to this issue, yes?
Yes, and I said that maybe signed.
So the solution would be for software developers to always use full pass when trying to load the DLLs. And making sure that if there is a system DLL which is loaded, then the system directory is the one prioritized. But hardly ever knows about the ordinary DLL injection problem, let alone the .NET one. So fixing this problem is kind of difficult, and we always see new binaries which are vulnerable to side loading and which will be abused by APTs, especially Chinese-speaking ones, because they love this technique. In almost every report about a Chinese-speaking APT, you see this trick being used.
Okay. No, but the one thing, we have digitally signed executables.
Yes.
Could we do the same with DLLs and prevent that?
This can also be a solution because, but only if you install a policy on your Windows machine that would prevent anything unsigned from loading. But it's also possible to bypass it.
Okay. Thank you.
The one back, black shirt, corner, long hair.
Thank you for the presentation. Could you shed some light for us on how EDR userland hooking of NTDLL is affected or affects this side loading?
Thanks a lot. So basically, this NTDLL.dll, it gets loaded alongside the system DLL. So if you install your hooks into NTDLL.dll and you get side loaded, then it doesn't get affected because the hooks stay still there. They're still in the system copy in the system DLL. So the hooks don't get removed, but in general, once you get side loaded, then you can remove almost every hook. You can unhook almost every library, and that's why it's very important to also use kernel side hooks if you're developing a security solution.
Thank you.
One more. Yeah.
First of all, congratulations for your presentation. Okay. Second of all, I had a case where a threat actor, first of all, moved the files moved the DLLs that he wanted to sideload, and after that, he inserted the DLLs in the protected path because he had administrator rights. What's your take on that? I think it's still Microsoft problems because it's shouldn't happen even if you have admin rights.
Thank you. So, as far as I understood, sorry, there's an echo here on stage. As far as I understood, you're talking about the fact that people are somehow, the threat actors are able to use administrative privileges to move DLLs into system locations, yes?
Well, they didn't move the files, they just renamed the DLLs they wanted to load, and after that they uploaded their DLLs.
Oh.
And because of and even though there was a full path most likely on the program that loaded them, they wouldn't load the correct DLL.
Oh, I see. But if it's a system DLL, well, what Microsoft says, like, the onus is on the owner of the machines to make sure that administrative privileges are never granted to a threat actor. So Microsoft doesn't admit its fault when it comes to DLL side loading. It thinks it's like ordinary behavior, and that it is the responsibility of the developers to make sure that the DLLs cannot be sideloaded, and that you do not allow anybody to tamper with the files like doing renaming. It's all about it's on the developer side actually. But we as security experts may of course blame anybody we want.
Thank you.